Hello everyone. So today I'm going to be guiding you through an end-to-end workflow of how I would take some 2D Western blot, 2D gel, 2D dye, whatever it may be, images, and use those to calculate my anti-host cell protein antibody coverage. Now, as I mentioned, SpotMap doesn't really care what experimental technique you've used. It will take in images from a classic 2D Western blot and 2D gel experiment, 2D dye or 2D dye experiment, and it will analyze them all the same. So the workflow that I'm going to be showing you today is applicable to all of the different experimental techniques in this space for host cell protein antibody coverage. Now, the kits you get from people like Cygnus, Rockland, people like that, they've all been validated using this method, the antibodies that they use. Some of them use our software. Cygnus, for example, use our SpotMap 2D software to validate their antibodies, which make their way into their ELISAs and into your hands. But if you are quite advanced in your process and you want a platform-specific ELISA, so you want to develop antibodies specific to your cell line in your conditions, this is the work you're going to have to do to validate those and to get your coverage score to be able to submit it to the FDA, for example, to show that you are accounting for and measuring the vast majority of the host cell proteins that could be in your sample. So, like I said, this is going to be a quick workflow, a quick run through of the workflow. I'm not going to go into incredible detail or do this quote unquote properly. Whilst SpotMap is able to generate you a coverage score from within like 10 minutes to an hour, which is, a quarter of the time of competitor software, it is still not the world's most interesting tutorial video for you, the viewer. So I'm going to show you the tools, I'm going to show you how we do it and explain some of the kind of rationale behind the tools. But if you have a look at this and say, oh, well, he's not accounted for every single spot or he's not split that spot there, that's not what this video is for. You would obviously take the time to do it properly and go through and do that yourself. So the first thing I'm going to do is actually import my images. So you can see here that I've brought two image files into this experiment. I've got one labeled with CY3, one labeled with CY5. So this is coming from a 2D dye or dye experiment, aka multiplexed experiment. It doesn't matter if you're not using a multiplexed experiment or 2D dye or 2D dye. The workflow is the same. So that's what you should take from this video, that this is how you would arrive at a coverage score using SpotMap. So I like to see all of the images that I'm working with in SpotMap on the screen at the same time. So I'm going to click this button on the right hand side, open image in new tab, and select, well, the only other image that is in this project. Now, SpotMap can handle lots of different images. It can handle 8, 10, 12 images if you want to do comparisons between different blots in the same gel, different gels, things like that, different kind of permutations of that. The only limitation is the amount of processing power your computer has. As you can imagine, opening lots of high resolution images with kind of lots of spots and then trying to perform analysis amongst all of those is quite taxing on a machine. So I'm just going to open two for now, but the process for importing and opening and displaying them all on the screen is all exactly the same. So I'm going to hold shift and zoom out to zoom out of my images. Sorry, to scroll my mouse wheel backwards to zoom out of my images there. And if you want to turn the 3D view off, if you find it somewhat distracting, you can do that from the display options section here on the right hand side. Now, the first step in the actual workflow is to detect my spots. So I'm going to come through and click on the detect spots button. So the shortcut for that is Q. Now, if I just click detect spots here, it's going to try and analyze the whole image for spots, which isn't going to give me very good spot detection because it will account for all these really dark areas of the images, this 1 mil here, this up here. So what I'm going to do is add a rectangular image, add a rectangular region to my image, which is a region, an area of interest that you should fit around your data as tightly as possible to give it the best chance and the most accurate kind of spot measurement or spot detection. You should note here that it says source image. If I want to change which image I'm doing my spot detection on, I can click the names up at the top here, these like little tabs. I'm going to work on initially on source image A. So for this kind of demonstration, source image A is going to be like my total protein stain. It's going to be the image that I have that represents all of the proteins that should be in my host cell, So kind of like your null cell line, something like that. The detection parameters here at the bottom, they are how you, the user, control the sensitivity of the spot detection algorithm. Think of peak sensitivity as a cutoff point, where any spot that has a peak above this number will be counted, and any spot that has a peak below it will be ignored. So if I make this 0, I'll get a ton of spots. If I make this 1,000, I'll get next to no spots because I've set my threshold very high. People often come to me and say, well, what should I use? What numbers should I use? Can you please tell me what numbers to put into this for my experiment? And it's impossible basically for me to give you a number from my side, from not having worked with your images or seen your images, to know what's going to work for you. So it's very much something that you have to do on the customer has to do on their side and calibrate it for their images. Now, saying that, if you have a very standardized process, your images always come out looking the same, your experiments always come out looking the same, then you might be okay to set this at one value and use it for every experiment that you do. Or you might need to change it for every experiment that you do. There's nothing wrong with that. And some people, it's always in the report what sensitivity settings you've used. It's saved in the project file, so you don't have to worry about kind of inconsistency really there. But if you do want to set a fixed value, you do have that option as well. So that's how peak sensitivity works. Now, smoothing essentially smooths the edges of the peak. It's like a noise filter. And you can adjust that up and down. The default is typically 1. You can adjust that up and down. If you set it to 4, you're going to get, let me think, fewer spots than you would if you set it to 0. But we can see that. See, we don't get many spots there, but if we set it to 0, we now get a lot more spots. So I'm just going to set this to 1. I'm not going to create a set of these spots. These settings down here, you don't really need to concern yourself with until later. And I'll explain those later when we come to do that step. So I'm aware that I've not detected every spot here. Again, the process is what you should take away from this, not the actual, analysis. So I'm going to come through and run my spot detection based on those settings, and then close this down. So now I can come through to my alignment step. Now, because these are DIGE or dive experiments, alignment's actually much easier than it would be if I was using a 2D gel and Western blot pair. First thing I'm going to do is set my alignment target to the image that represents my 100% of my host cell proteins. So in your gel and blot pair, that would be a gel. In your 2D DIGE and dive experiments, it would be the channel, the multiplex channel, the dye channel that aligns with your total host cell protein fraction. So for me, I'm going to pretend that's A, as I mentioned before. I'm going to pretend my image A is my total protein stain, my 100% value, and then I'm going to click on Align. So then I'm going to be greeted with this window. Now, I'm not going to go through the whole alignment process because I have a separate video on that. I don't want this video to be an hour long. So please check out that video if you want to understand more the nuances and how you validate your alignment and things like that. For the moment, I'm just going to use the automatic alignment tool. Now, automatic alignment tool is really good for DIGE and dive images because there's very little alignment to be done. You do still need to align them, and it is still important to align them to get rid of any kind of positional variation or shifting that's happened. But it's a minimal alignment. It's a very small level of alignment here versus what you would typically get in a 2D gel and Western blot pair. So I'm going to say I'm happy with that alignment and then click OK. And you won't have seen it there because it's really quick, but this image has now slightly moved or changed to match using the alignment vectors that we included there to match this image. So we're now working on an aligned image. So the next step is to start actually calculating our coverage. So first we need to select our coverage target, and again, this would be your 100% host cell protein, your total protein stained, your maximum, what you would expect to be your maximum 100%. For me, that's image A. So what I'm going to do is I'm going to left click and drag all these spots, and you'll see I select them on both. Now, the way SpotMap works and the way you should consider it is these spots that I've detected on image A, I've overlaid them on image B. I've not detected them on image B. There's not been a spot detection run here yet, but this template shows me where if I had 100% coverage, this template is where spots should be on image B. So what I'm going to do is I'm going to mark them as, they're automatically marked as present on image A because that's where they were detected. I'm going to come through to image B and I'm going to mark them all as present. So now this is theoretically 100% coverage. What I'm going to do now is I'm actually going to use filters to kind of exclude any spots that should have been there but weren't. Now let me explain how I'm going to do this. So although I said this is just a template that is overlaid, the software is still taking measurements from these outlines. So I can actually search within all of these using a filter and remove anything that actually isn't there. So where there's an outline, where there's a spot, should be there, but there isn't. And I'm going to use an example of, let's say our image cutoff should be, we're going to say anything fainter than this, collection of spots here, I'm going to say isn't there, isn't present, isn't a true spot. If I turn on my 3D views, we can see this area, this spot area is, very small, it's very faint, it's probably not a true positive spot. So I'm going to filter out, I'm going to mark everything with a value with a peak value of this and below as absent, so not picked up by my antibody. If I click match spots by filter, so I'm on image B and I need to add a criteria to this filter. Now I'm just going to filter by peak height, aka how high this peak is, how strong this signal is, but you can filter by all of these different parameters and you can add them as well. So you can filter by volume and area, things like that. So I'm going to go for peak height, and if I click this number here, I can actually use the value from the spot that I've got selected. So now that's given me the intensity value, the peak height value for this spot, and I want to exclude anything with a value equal to or less than this. So clicking select matching spots will select all of them in the image, of which there's not a huge amount, and I'm going to use this button here to select them as absent. You can see here now my antibody coverage has gone from 100% to 95% because spots that should be there aren't. And you can do this manually, of course. You can click these, you can just click these with your selection tool. And then mark them as absent, but using filters you can do it really, really quickly and set up your kind of cutoff and your parameters for selection. So I could do this manually here, just select a few of these, and you can see my coverage score is starting to change based on the fact that my antibody has missed spots that it should have detected if it was detecting all of them. Another thing you can do is also, so with that process we've checked what our antibody has detected that it should, but it hasn't. What about the inverse? Has our antibody detected anything that it shouldn't have done and included that as a spot, as a readout, as a measurement? So if I click detect spots again, and I come through to my source image being image B, what I can do now is run a spot detection in the same area with the same kind of settings, or you can change the settings as well, but with the same kind of settings for the for this experiment, these images are very similar. I'm going to keep the spot detection settings the same, but I can use this include only new spots to leave all the spots there that I've already got, my spot outlines, but add in any spots that are present in this spot detection that weren't present already on my image. So I'm telling the spot detection algorithm to only include new spots when performing this. And overlap resistance applies to, well, it says exactly there, when including new spots, specify how much of a new spot's area is allowed to be overlapped by an existing spot before we don't consider it a new spot, basically. I would always leave this at medium unless you're working with, lots of new spots that also collide with existing spots, like overlapping spots. And if we click on create set, we can actually create a set from new spots generated in this detection, which can allow us to kind of group them and consider them. But I've got a separate video on using spot sets and things like that that you can feel free to go and check out. I'm not going to dive into it on this video. So if I click on detect spots, you'll see that my coverage score has changed because SpotMap has actually identified a load of new spots. Oh, sorry, it's not that group. This group. Neither of these groups because I didn't include it in the set. SpotMap has now detected a ton of new spots that it didn't detect before in this image. So these are labeled in purple, and these have been removed from the coverage score. So these are spots whereby there's been some kind of contamination, or my antibody has, got some non-specific binding to something on my image. Whatever it is, the antibody is bound to something that is not registered with the total protein stain as a host cell protein. So this is spots that are there that shouldn't be there. So again, this impacts our coverage because we want to be really accurate with what we're saying as the results of this experiment. The question we're trying to answer is, out of all of our host cell proteins, how many does our antibody bind to? We're not concerned with things that our antibody binds to that are not the host cell protein that we're considering. So although this is information, and it's definitely information that should be followed up, whether it's contamination or non-specific binding or something else like that, it doesn't impact what we want to know at the end of this experiment, which is, again, how much coverage does our antibody have for our host cell protein out of 100%. So now you can see we're coming out with 82% coverage. This is a whistle-stop tour of how to use 2D techniques to get an antibody coverage that you would then use to validate your ELISA or whatever you're going to use your antibody in, and then also for regulatory submission to the FDA to prove your antibody coverage. Still the gold standard to use 2D techniques at the minute for determining host cell protein coverage. From here, the next step would be to produce a report using the data access tool in the burger menu up the top here. Now, I have another video which is again more in-depth, more detailed about exporting high definition images, exporting reports, like what you do with the information now that you've got it. Please check that out because I don't want this video to be an hour long because no one's going to watch it, no one's going to read through it. But yeah, if you've got any questions, if you've got any specific help that you want, if you're an existing customer or you're a potential customer, please reach out to us, leave a comment on the video, leave a comment on the channel, get in touch. We'd be happy to help you out with any specific questions that you may have. And as always, if you want to try out a free trial of our SpotMap software in your lab with your own images, please check out the link in the description below.